The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. All right, today we're going to go on to section 9.3, but first of all, we have several questions from section 9.2. So we'll start with those. This first question, this is problem number 24. It says, simplify the expression. The variable represents a positive real number. What that last piece of instructions tells us is that we don't need to worry about absolute value because we're told the variable represents a positive real number. And we have the following. Negative 8x cubed over 27, all to the negative 1/3 power. The first thing I'm going to do is take that outside power and make it positive. And I'm going to do that by taking the reciprocal of what's inside the parentheses. And now that becomes raised to the positive 1/3 power. Next, I'm going to attach that outside power to each of the numbers inside. I'm going to go ahead and do this. I'm going to take that negative sign and just put it with the 27. Okay. I could treat it separately as a -1, but I'm going to treat it as a -27. So now I've got the following. I've got -27 to the 1/3 power over 8 to the 1/3 power times x cubed to the 1/3 power. Well, -27 to the 1/3 power, that's like the cube root of -27, which would be -3. -3 times -3 times -3 is -27. In the denominator, we've got 8 to the 1/3 power. The cube root of 8 is 2. Then we've got x cubed to the 1/3 power. A power raised to a power, you would multiply the exponents. 3 times 1/3 is 3/3, which is 1. So it's x to the 1 or just x. So there's our answer, or you could write it like that. So either like this or like that. Any questions on that problem before we go on to the next one? Okay, next up, still from 9.2 is number 27. It says, simplify the expression, write the answer without using negative exponents. And that's pretty much standard, even if it didn't say that you don't want to write an answer with negative exponents. The only exception to that, two exceptions. One, if you're using scientific notation, sometimes it has times 10 to a negative power, or if the directions specifically say to use negative exponents. Otherwise, we always write it with positive exponents anyway. All right, so simplify the expression. 2 to the 7/20th power times 2 to the 1/5 power, all over 2 to the 1/4 power. Well, on top, we're multiplying two powers with the same base. So we're going to take the base and add the exponents and attach them to it. So this is going to be 2 raised to the 7/20th plus 1/5 power. Okay, now let's take 7/20th plus 1/5. The common denominator there would be 20. So we're going to multiply 1/5 by 4/4. So 1/5 becomes 4/20. 7/20 plus 4/20 is 11/20. So we now get 2 to the 11/20 power over 2 to the 1/4 power. Any questions so far? All right, but now we're dividing two powers with the same base. So we're going to subtract the bottom exponent from the top exponent and attach that to the base. So I've got 11/20 minus 1/4. Common denominator there would be 20. Going to multiply 1/4 by 5/5. So I get 11/20 minus 5/20, which is 6/20. which is 3/10. So we get 2 to the 3/10 power, and that's our final answer. All righty, that takes us to number 28. And again, these are all from section 9.2. Perform the multiplications. The variable represents a positive real number. Simplify your answer completely. So we've got y to the 1/3 power times the quantity y to the negative 1/3 plus y to the 2/3 power. So we're going to distribute. We're going to have y to the 1/3 power times y to the negative 1/3 power plus y to the 1/3 power times y to the 2/3 power. Multiplying two powers with the same base, we add the exponents. So here we get y to the 1/3 plus negative 1/3. 1/3 plus negative 1/3 is 0. Y to the 0 power is just 1. And then here, y to the 1/3 times y to the 2/3 would be y to the 1/3 plus 2/3, which is 3/3, which is y to the 1, which is just y. So our final answer, 1 plus y. Or you could write it as y plus 1, either way. All right, let's see. Next up is 32. Simplify the expression. The variable represents a positive real number. So we've got a negative outside of b to the 8th over 625, all raised to the 3/4 power. The negative sign is not inside the grouping symbol, so it's a total different factor, so to speak. So this would be a negative, and then b to the 8th to the 3/4 power over 625 to the 3/4 power, which is negative. Well, let's see. B to the 8th to the 3/4 power, a power raised to a power, you would multiply the exponents. 8 times 3/4 reduces down to 6 over 1, or just 6. So we're going to have b to the 6th power on top. 625 to the 3/4 power. 625, I'm going to take the 1/4 power, so take the 4th root and then cube the results. Well, the 4th root of 625 is 5. And if you don't just know that or see that, you could put this into your calculator. 625, the little caret key raised to the 1/4 power. Let's see, got to turn it on first. 625 to the parentheses, 1 divided by 4 power. And that becomes 5. And then that's going to be cubed, which is 125. So there's the final answer. Or you could write it like this, negative b to the 6th over 125. But again, that negative sign is outside the original part. Let's see, 34 coming up. Number 34. Simplify the expression. The variable represents a positive real number. Very similar to one we did a little earlier. C to the 3/5, c to the 3/5, c to the 1/5. At least these all have the same common denominator. So multiplying two powers with the same base, add the exponents. 3/5 plus 3/5 is 6/5. So we get c to the 6/5 on top. Dividing two powers with the same base, we subtract the bottom exponent from the top exponent. So we get c to the 6/5 minus 1/5, which is 5/5, which is c to the 1, which is just c. Okay. 37 coming up. Simplify the expression. T to the 4/3 power times t to the 8/3 plus t to the negative 4/3. So again, one similar to this, we distributed, so we get t to the 4/3 times t to the 8/3 plus t to the 4/3 times t to the negative 4/3. T to the 4/3 times t to the 8/3 would be t to the 12/3, which is t to the 4th. T to the 4/3 times t to the negative 4/3 would be t to the 0 power, which is 1. So your final answer, t to the 4th plus 1. Let's see, number 40. Let's see here, where did it go? Number 40. All right, I just do, yeah. Simplify the expression, the variable represents a positive real number. We have the 9th root of 27x to the 6th. Okay, so what we're going to do here is we're going to change this into exponential notation, and then we're going to simplify it. So 27 to the 1/9 power. Well, here's the thing, and this is something you may not have thought of before, but hopefully you will in the future. 27 itself could be written as 3 cubed. Okay, so 27 to the 1/9 power is 3 cubed to the 1/9 power, but now we have a power raised to a power, so we'll multiply the exponents. 3 times 1/9 is 3/9, which reduces to 1/3. So I've now got 3 to the 1/3 power. Okay. X to the 6th to the 1/9 power. You'd multiply the exponents. So that's going to be x to the 6/9, which is x to the 2/3. Now, this is where things get a little bit tricky. I could write this as 3 to the 1/3 times x squared to the 1/3. Pulling this apart. So now I've got the cube root of 3x squared. Yeah, that's kind of a tricky one. And as we learn more of the rules, that will get easier to do. But for right now, we've got that situation. And finally, number 42. Simplify the expression. The variables represent positive real numbers, negative the quantity. 16 s to the 8th t to the 6th all to the negative 3/2 power. So this is going to become negative 1 over 16 s to the 8th t to the 6th all to the positive 3/2 power, because this is like that over 1. So then I've got negative 1 to the 3/2 power over 16 to the 3/2 power s to the 8th to the 3/2 power, t to the 6th to the 3/2 power. Okay. 1, the square root of 1 is 1. 1 cubed is 1. So we get a 1 in the numerator. Okay. So that whole thing becomes that. Then 16 to the 3/2 power would be 16 to the 1/2 power cubed, which is 4 cubed, which is 64. S to the 8th to the 3/2 power, a power raised to a power, you multiply the exponents. 8 times 3/2 is 24/2 is 12. So s to the 12th. And then t to the 6th to the 3/2 power, a power raised to a power, you multiply the exponents. 6 times 3/2 is 18/2 or 9. So we got t to the 9. So final answer, negative 1 over 64 s to the 12th t to the 9th power. And there you have it. All right, we're going to go on to the next section now. So here we go on to section 9.3. We have 2 rules that we're going to look at in this section. They aren't new, but radical notation is new. Let's take the following. Let's say we have a product raised to a power. Well, back in chapter 5 in a class called Math 85, or maybe in a beginning algebra class, we learned, and I also reviewed this yesterday, a product raised to a power, you attach the outside power to each factor of the product. So the quantity AB to the n could be written as A to the n times B to the n. Well, what if the exponent instead of n was 1 over n? Well, then you'd have A to the 1 over n times B to the 1 over n. Still, you with me so far? Well, let's translate this situation into radical notation. That would be the nth root of A times B equals the nth root of A times the nth root of B. So what that is saying is, if we have a product radicand, we can pull apart the separate factors and each one of them will have the same index as the original. So for instance, the square root of 36 could be written as the square root of 9 times 4, could be written as the square root of 9 times the square root of 4, if we so chose to do that, okay? 36 is 9 times 4. I can take this and write it like that and then deal with each one of these separately. Square root of 9 is 3, square root of 4 is 2, 3 times 2 is 6. Of course, in this example, you could go straight there anyway, but I'm just wanting to show you how that works. So if we have a product under the radical, we can separate the different factors, each under a radical with the same original index, okay? Second rule, another one we've already had. Let's say I have a quotient raised to an outside power. I can attach the outside power to both the numerator and the denominator of the quotient. Likewise, if I had something like this, A over B to the 1 over n power, I'd have A to the 1 over n divided by B to the 1 over n. Writing this in radical notation, that would be the nth root of the quotient A over B, which would then become the nth root of A over the nth root of B. So if I have a quotient under a radical, I can separate the numerator from the denominator as different radicals, but all with the same index as the original. Okay, so we're going to use those two rules to do something called simplifying a radical. Now, I don't know about you, but when I think of simplifying something, I figure that what I get when I'm done is going to be easier. It's going to look nicer than what I started with. That's not necessarily the case with simplifying a radical. Simplifying a radical means that you're going to take everything that you can out from inside the radical and get it on the outside. Okay, that's what simplifying the radical means. Now, give me a second here. Let's say we have the following situation. We have the square root of 50, and it says simplify each expression. So what I want to do is get everything I can outside of the radical. The index is an implied 2, so we're taking the square root. So what we want to do is we want to take 50 and write it as perfect squares and leftover factors. So for instance, 50 could be written as 25 times 2. Then using this rule, I can split it apart like that, okay? The square root of 25 is 5. The square root of 2 is still the square root of 2. So I get that. So the square root of 50 simplified is 5 times the square root of 2. Again, that doesn't look nicer, does it? No, but that's what's known as simplifying the radical. We found all the perfect square factors and unsquared them, kicked them outside. Any questions about this particular example? All right, now let me go back for a minute. I could have also done this, but that's not useful because neither of those are perfect squares. The index, or in this case, the implied index of a 2, tells us how we want our factors to look. We want perfect square factors so that we can undo them and kick them outside. All right. How about this one? The square root of 28. That could be written as the square root of 4 times 7, which could be written as the square root of 4 times the square root of 7. The square root of 4 is 2, so I have 2 square roots of 7 as my final answer. 7, I can't take the square root. I can't break apart any square factors from it, so it's stuck inside. We okay with this? Well, I'll assume we are.
Yes.
Okay, good. How about this one? 9 square roots of 54. So the 9 is being multiplied by the radical. It's outside. We don't have to do anything with it. But 54 is 9 times 6. 9 is a perfect square. 6 is 2 times 3. So that isn't going to get us anywhere. But we could rewrite this like this. Okay. Then we could split apart. Oops. And write 9 times the square root of 9 times the square root of 6. Again, 6 breaks down to 2 times 3, so there's no perfect squares there. So this is going to be 9 times 3 times the square root of 6, because the square root of 9 is 3 on the outside. Then 9 times 3, 27, square roots of 6. Final answer. All right with that? Questions? Okay. Cube root of 40. Well, now my index is a 3, so I'm taking the cube root. So I want to look for factors that are perfect cubes. Well, 40 is 8 times 5. 8 is a cube. So I could write this like that. And then pull it apart like this. The cube root of 8 is 2 outside, so I get 2 times the cube root of 5. Now, that's doing it the quick way because I knew that 8 was a cube and that 8 was a factor of 40. Let's say that that isn't something that you see really quickly and really easily. So let's look at how we could deal with this a different way. Okay. Well, we could say 40 is 2 times 20, and 20 is 2 times 10, and 10 is 2 times 5. So basically what I'm doing is the prime factorization. Oh, look, there's a cube and some leftovers. So I could write it like this, and then I could write it like this. The cube root of 2 cubed is 2, and I get 2 cube roots of 5. Okay with that? Are you okay with the cube root of 2 cubed is 2? Because wouldn't that be 2 to the 3/3 power, which is 2 to the 1, which is 2? Okay. Move on just a second. Right. Let's take a look at this one, the 4th root of 32. So now I'm looking for, I don't know, is it fourples, something to the 4th power? Well, 32 is 2 times 16, which is 2 times 2 times 8, which is 2 times 2 times 2 times 4, which is 2 times 2 times 2 times 2 times 2, or 2 to the 5th power. Well, I could write that as 2 to the 4th times 2 to the 1 power. Which could then become the 4th root of 2 to the 4th times the 4th root of 2 to the 1 power. The 4th root of 2 to the 4th is 2, and then you've got the 4th root of 2 to the 1, and I don't really need to put the 1 exponent there. This brings up another rule, and that is the nth root of a to the n equals a if a is greater than or equal to 0. What am I saying there? That if the index matches the exponent inside and the base is not a negative number, these two have the effect of reducing out, because think of it this way. The nth root of a to the n would be a to the n over n, which is a to the 1, which is a. Okay, we're going to use that a lot. All right. says simplify each radical expression. All variables represent positive real numbers. Excuse me. So we don't have to worry about absolute value. All this water, I'm living in a swamp. I've got frogs here. So let's see. What I could do is I could break that down into 25 times 2 times x squared. So I've got a square and leftovers. Okay. I could rewrite that as the square root of 25 times the square root of 2 times the square root of x squared. The square root of 25 is 5. The square root of 2 is still the square root of 2. The square root of x squared is x. Putting all the non-radical stuff together, I get 5x times the square root of 2. There's my final answer. Any questions about that? All right, now, what I want to do next is kind of shortcut the process. And that is, when I've got it in this form, rather than write it like this and like this, I'm just going to go in and say, well, the square root of 25 is 5, the square root of x squared is x, and I've got the square root of 2 left over, and do it like that, rather than writing it as separate factors. Are you okay with that?
Yes.
Okay, great. Let's see here. We've got the square root of 75 b to the 8th power c. Well, I could write this as 25, that's a square, times 3 times b squared times b squared times b squared times b squared times c. Now, what did I just do? I took all of the b's and wrote them as squares, and then if there were any leftovers, because again, my implied index is a 2, right? 25 is a square, and then all the b squareds are squares. So doing that, I would get this. That would give me a 5 outside. That would give me a b outside, a b outside, a b outside, a b outside, and what's left inside would be the square root of 3c. So I get 5 b to the 4th, whoops, square root of 3c as my final answer. However, that seems like a lot of work. So consider this. The square root of b squared, again, we're assuming the variables are all positive, is b, right? What's the square root of b to the 4th? Isn't that b squared? And the square root of b to the 6th would be b cubed. And the square root of b to the 8th would be b to the 4th, right? So if our exponents on the variable are either a match of the index or a multiple of the index, so 2, 4, 6, 8, 10, 12, whatever, I don't need to break it all down like that and like that. I could just tackle that individually and say, oh, that's going to be b to the 4th outside. So what would that look like doing it a shortcut way? Let's see here. It would look like this. This would give me a 5. This would give me a b to the 4th. And then I'd have 3c left inside. All right with that? Let's see here. Let's take a look at this one. It says simplify each radical expression. All variables represent positive real numbers. The square root of 363. Well, let's see. 363. 3 goes in 121 times. I think that's right. Let's see. 363 divided by 3 is 121. 121 is 11 squared. So I could write it like that. Okay. What's the square root of 11 squared? That's 11 outside, and what's left inside would be a 3. So 11 square root's a 3. Okay with that? Finally getting warm enough around here. How about this one? The square root of 147 a to the 5th. All right, 147 is 7 times 21, which is 7 times 7 times 3, which is 7 squared times 3. So I'm going to rewrite this as 7 squared times 3 times, and I'm going to take a to the 5th and write it as a to the 4th times a to the 1. Why did I break it apart like that? Because remember, I want exponents that are either matches of the index or multiples. Well, the highest multiple of 2 is 4, right? Because the 5 doesn't go in and I can't go on to 6. So now that's going to give me a 7 outside. That's going to give me an a squared outside, and I'm going to have 3a left over inside. Are you picking up what I'm putting down here? Are you getting this?
Yes.
All right. Let's see here. Let's do, how are we doing for time? Let's see. Let's do one more of these. We've got the cube root of 280 a to the 5th, b to the 6th. So 280 is 28 times 10, is 2 times 14 times 2 times 5, is 2 times 2 times 7 times 2 times 5, is 2 cubed times 5 times 7. So there's the prime factorization of 280. Notice I've got a cube and leftovers. So 2 cubed times 5 times 7. A to the 5th, I'm going to write as a cubed times a to the leftovers. I can't get to a to the 6th, right? But b to the 6th, I'm going to leave alone because 3 goes into 6 evenly. So I broke it apart into cubes or powers that are multiples of 3 and then leftovers. So the cube root of 2 cubed is 2 outside. The cube root of a cubed is a outside. The cube root of b to the 6th is b squared outside. And left inside is 5 times 7, 35a squared. And typically we take what's inside and multiply it back together rather than leaving it separately. All righty. Now let's take a look at this. It says simplify each radical expression. All variables represent positive real numbers. So I've got the square root of 3/4. So that's equal to the square root of 3 over the square root of 4, which is equal to the square root of 3 over 2. So basically, if we have a fraction inside a radical, we can separate the numerator from the denominator and deal with them separately. Okay. And let's take a look at this one. The 5th root of 2 over 243. So that's the 5th root of 2 over the 5th root of 243. Well, 243 is 3 times 81, which is 3 times 9 times 9, which is 3 times 3 times 3 times 3 times 3, which is 3 to the 5th power. So I've got the 5th root of 2 over, what's the 5th root of 3 to the 5th power? It's 3. Because the exponent in the index reduced down to 1 over 1. 3 to the 1 power is just 3. Okay. How about this? The square root of 128 over the square root of 2. Well, just like we can take a fraction under a radical and split it up, if we have a fraction of two separate radicals, if they have the same index, which these do, we could put them together as a single radical. Well, then 128 over 2 is 64, and the square root of 64 is 8. So we can put them together or we can pull them apart. Okay. Questions about that one? All right, let's say I've got the square root of 75y to the 5th over the square root of 3y. Well, that's the square root of 75y to the 5th over 3y, which is the square root of 25y to the 4th, because 75 over 3 reduces to 25. Y to the 5th divided by y to the 1 is y to the 5 minus 1, or y to the 4th power. Okay. Well, then from here, the square root of 25 is 5, and the square root of y to the 4th is y squared. So there's your final answer. Okay with that? All righty. 2x plus 3x equals 5x, right? Because we say these are like terms. 2 square roots of 5 plus 3 square roots of 5 would be 5 square roots of 5, because these are like radicals. The radical part of each term is the same. So 2 of them plus 3 of them would be 5 of them. Or 3 square roots of 7 plus 2 square roots of 7 would be 5 square roots of 7. But 3 square roots of 7 plus 2 square roots of 5, we can't put those together. They're not like radicals. All right, now, this next set of directions says simplify by combining like radicals. 11 square roots of 3 plus 2 square roots of 3. These are like radicals, so that would be 13 square roots of 3. Any questions there? 30 cube roots of 6 minus 10 cube roots of 6 would be 20 cube roots of 6, because those are like radicals. So far, so good?
Yes.
All right. Now, what if we have something like this? 9 plus the square root of 45 plus the square root of 20 plus 16. Well, the 9 and 16, they are alike, but the square root of 45 and the square root of 20 don't appear to be like radicals yet. What we need to do first of all is simplify each radical term. Let's take the square root of 45. That's the square root of 9 times 5, which would be 3 square roots of 5. Right? So the square root of 45 could be written as 3 square roots of 5.
Yes.
The square root of 20 is the square root of 4 times 5, which is 2 square roots of 5. So once we've simplified them, they are like radicals. So now I've got 9 plus 16 is 25 plus 3 square roots of 5 plus 2 square roots of 5, which is 5 square roots of 5. And I can't combine the 25 and the 5 square roots of 5, but I can go that far with it. So the key here, simplify each radical first and then combine the like radicals. We good?
Yes.
All right. How about this? The square root of 20 plus the square root of 125 minus the square root of 80. Well, the square root of 20 would be the square root of 4 times 5, which is 2 square roots of 5. The square root of 125 is the square root of 25 times 5, which is 5 square roots of 5. And the square root of 80 is the square root of 16 times 5, which is 4 square roots of 5. So once I've simplified all these radicals, they are in fact all like radicals. 2 of something plus 5 of something is 7 of something. 7 of something minus 4 of something is 3 of something, the something being the square root of 5. All right, with that. We good to go?
How do you got the 3 over 5? The 3?
Where did I get the 3?
Uh-huh.
2 of something plus 5 of something is 7 of something. 7 minus 4 is 3 of something.
Oh, yes, yes. Okay, thank you.
You bet, you bet. All right, we good to go on?
Yes.
12 plus the cube root of 80 minus the cube root of 10, whoops, 10,000 plus 4. The cube root of 80 still didn't make that very good. The cube root of 80 would be the cube root of 8 times 10. The cube root of 8 is 2. So this is going to be 2 cube roots of 10. Okay, so 3 cube roots. So the cube root of 80 is 2 cube roots of 10. And then the cube root of 10,000 would be the cube root of 10 to the 4th, because yeah, because 10,000 is 10 times 10 times 10 times 10. But that's the cube root of 10 cubed times 10. The cube root of 10 cubed is 10 outside, so I get minus 10 cube roots of 10 plus 4. So again, this simplifies into that. This simplifies into that. And now these two are like terms. So I've got 12 plus 4 is 16, and then plus 2 cube roots of 10 minus 10 cube roots of 10 is minus 8 cube roots of 10. I'm just having all kinds of fun with all these different colored pens. You okay with that? Any questions there?
Will you be able to do another one of this one?
I will. Here we go.
Thank you.
23 fourth roots of 3 plus the fourth root of 48. Well, the fourth root of 48 is equal to the fourth root of 16 times 3. 16 is 4 times 4, or 2 times 2 times 2 times 2. Okay, so that's the fourth root of 2 to the 4th times 3. The fourth root of 2 to the 4th is a 2 outside. So basically what I can do is change this into that by simplifying the radical. Now they are like radicals, and you'd have 25 fourth roots of 3. Let's go back for a minute and look at this. I knew that 16 was 2 to the 4th power. Let's say I didn't know that. 48 is 2 times 24, 2 times 2 times 12, 2 times 2 times 2 times 6, 2 times 2 times 2 times 2 times 3, 2 to the 4th times 3. Okay, so the 4th root of 48 is the 4th root of, well, all the way down here, that. Okay, the 4th root of 2 to the 4th is a 2 outside, and I've got a 3 inside. And that's where I got that, which then combined with that to give me that. So you're simplifying each radical first. You okay with this one?
Yes.
Look at another one. Square root of 98 minus the square root of 50 minus the square root of 72. 98 is 49 times 2. So the square root of 49 times 2 would be 7 square roots of 2, because the square root of 49 is a 7 outside. Square root of 50 would be the square root of 25 times 2. Square root of 25 is a 5 outside, so we get minus 5 square roots of 2. The square root of 72 is the square root of 9 times 8. Oh, let's see here. The square root of 9 times 8, that would give you a 3 square roots of 8, except that 8 could be written as what, 2 cubed? So 2 squared times 2, that's going to give you an additional 2 outside. So you get 6 square roots of 2. So actually the perfect square here would have been 36 if you saw it, but I found it the long way. It's like, okay, 9's a square, but 8 breaks down even further. 7 minus 5 is 2, minus 6 is negative 4 square roots of 2. All right with that?
Yes.
All righty, well, time's just about up. I'll be back this afternoon at 1:15 with an office hour. If I don't see you there, I'll see you tomorrow. Thanks for stopping by.